We're going to explore more about the internal structure of minerals. The main heading for today is coordination number. And in the textbook, coordination number starts a new chapter, starts at page 66, goes into the 90s, but really the meat of the chapter is between 66 and 80. Now, as we get into coordination number, it's all about chemistry. And so we need to do a chemistry review. Or maybe I should say you should do a chemistry review, because we are not going to cover it in mineralogy. It's one of the prerequisites for this course. But here's a periodic table I snagged from Wikipedia. And so as you look at this, I need you to be able to recognize, the symbols. Why are they in their positions? Right? What does that mean about the amount of electrons they have in their different outer shells? What is this number, right? And what does it refer to? A lot of periodic tables show other additional numbers down here. What are those and what do those refer to? Well, all about the protons and the neutrons and the bonding. And so if you need a review on that, please go to your textbook, pages 37 to 64, to get a mineralogical review on chemistry. If that's not quite enough, then go to Wikipedia and go to Khan Academy and find the lectures that you need to make up the ground to understand topics like just what is an atom and the protons and neutrons, the electrons, what is atomic mass, what is an isotope. All right, these are just words I'm quickly writing down. They're ones I'm expecting you to understand. When I talk about atomic radii later in this lecture, you need to know what that means and what controls it. Valence state. What other things? Oh, bonding. There's all these different types of bonding that we're not going to review in this class, but that matter so much in mineralogy. The different types of bonding like ionic, covalent, metallic, van der Waals, and hydrogen bonding control things like mineral hardness and strength and resiliency and other properties. Okay, so that's a review you need to know before moving on here to Roman numeral 2, which is today's lecture, and it is the concept of the coordination number. Coordination number. We'll put a definition here first. I'll read it to you and then write it down. It is the number of closest neighbors that can surround a specific atom. Now I'm going to write that down in just a second with you. As we do that, let's let this just kind of sit below us on the page, where this candy, delicious candy, is our different atoms. And we got to think about how many atoms can be surrounded by others if you were to pack them and stack them very regularly, unlike this delicious pour out of little candy here. Okay, so coordination number is the number of closest neighbors, right? In our picture, it's the closest neighbors of candy, but in our minerals, it's the closest numbers of ions that surrounds a specific atom. In the textbook, the key figure is on page 72. So if you just have like 2 minutes to study and you want to study coordination number, go to page 72 and take a look at that figure. So let's start off our notes under coordination number as we talk about the significance of it with a drawing. And we're going to do two different drawings. One here is going to have a large center ion that is surrounded by as many ions as we can around it. Now, if I do this correctly, we can draw 6 around it. Make the circles the same size if possible, okay? And so if we want to do what's called, this would be called the closest packing in just 2 dimensions. The best you can ever hope for is to get 6 anions surrounded 1 cation. Okay, that's the best. And there's another scenario. I guess we should ask this, okay? What is the difference between these 2 drawings? And in this case over here, here's our cation. And if we were to do closest packing on this, we would get 1, 2, 3. All right, what's the difference between these two drawings? Well, the answer is the size of the cation, or that atom, on the inside, okay? So our answer to this question is size of central atom. And that ends up being the biggest control for coordination number. Another way to think about it is with this word of packing, right? How much packing can you get in order to get these outer circles touching themselves and also touching the interior? Okay, so that is what we need to talk about now more quantitatively. So we can go now into the third dimension, and in the third dimension we have our is what all our minerals have, and so we care about what is the maximum, and the maximum amount of packing you can get around a central cation in 3 dimensions is called 12-fold coordination. You can actually get 12 different cations or anions surrounding a single cation. I keep saying that these outer ones are anions and the central one is a cation, and because that's the way it actually plays out. But the textbook starts by talking about them as just atoms. All right, so 12-fold coordination means that in 3 dimensions you have touching 12. The central is touching 12. And how would that look? Well, if this is your central cation, you can get 3 above it, 3 below it, and then 6 surrounding it, and that adds up to 12. Now this is actually a fairly rare type of packing, rare packing in minerals. And the reason why is you have to have that center cation be exactly the same size as the anions, and that's rare in minerals. Okay, so we're just going to say that it requires same size for all atoms. So maybe if your mineral was gold and the center was gold and surrounded it was gold, well then you'd get that closest packing 12. Let's keep going through here. I want to introduce a little bit of math for you, how to figure out if you don't have a perfect 1-to-1 ratio between the size of the cations and the anions, what type of packing do you have? Well, that introduces to us the idea of the radius ratio. And so what we're going to do here is we're going to label this radius ratio. And the radius ratio is a fairly simple equation, and it is just the cation radius divided by the anion radius. And that's going to give you a number. And there are these thresholds that then set up based on the relative sizes of the cation and anion. So let's do this little one. The possibilities of coordination number. Can I just write C dot N as coordination number? Well, the possibilities of coordination number can be 12, 8, 6, 4, 3, and 2. And each one of these different types of packing, this is our closest packing that we just talked about before, where there was 1 cation surrounded by 12 anions. They're the same size. Well, here they're very different size when you just get to the coordination number of 2. This would be a very, very little cation and very big anions, and we'll show you that in just a second. Let's just do one example of the radius ratio. So let's go to number 2 here. This is our example. Our example is going to be done in the mineral fluorite. Fluorite has a chemical formula of CaF2, and that means we can break it down into its cation, calcium 2+, and fluorine. There's 2 of them, but it doesn't really matter for this. And that's a 1-, and the atomic radius of calcium is 1.12 angstroms, and the same for fluorine is 1.31, a very messy 1.3, there it is, 1.31 angstroms. So if we set up our radius ratio equals the cation 1.12 divided by 1.31 gives us an answer of 0.86. Now, if I don't know what the thresholds are to take this radius ratio and turn it into one of those numbers, then here's where I'm stuck. Well, that's what we're going to go do, and the answer in the end is going to be that this gives us an answer of cubic coordination, which has a packing of 8. You can't know that without me telling you what comes next, so don't worry about that. And so with that information, just from doing that one little radius ratio, we can figure out what the atomic packing looks like for fluorite. And it end up looking like this. We have our cube. We've drawn this many, many times. And sitting inside the center of that cube is going to be 1 calcium 2+. And then 8 fluorines are going to be packed around it. All right, this is all the information we just got from the coordination number. And things have to like electronically balance, right? And so what ends up happening is the fluorine 1 minus, each one of them gives like 1/4 of a minus charge in to balance off the 2+ sitting here in the middle. That's all this really important chemistry information that we can learn about minerals just from doing coordination number. All right, so what we're going to need to do now is we're going to make a table that points you towards that answer. And so what we're going to do is we're going to call this table, we're going to go D. This is going to be called thresholds for coordination. Thresholds for coordination. And as we draw this table, what I want to have happen is there's going to be 5 columns. Here, at least in my notes, we have over here we have radius, ratio, a line, and then we'll have number. So this is actually our coordination number. And then there's got to be an adjective to describe that coordination number. So we're going to call that name. It's the adjective. Then how about a geologic, a mineralogic example that has that. And then finally we're going to do a drawing of that, the appearance of that coordination. So to start, we're going to start with the lowest number. The lowest number has a coordination of 2. We call this structure linear. It has a radius ratio of less than 0.155. Our example is, there really isn't any. We're just going to put down here that it is very rare. And it's very rare because it has to be a very small, we'll say requires very small cation. Our drawing would be something like this. A really tiny cation surrounded by, and draw the circles as big as you can, 2, whoops, that black dot's supposed to be right there at the touch point between them. Okay, 2 really big anions. All right, so there's our example. And we don't really see that very much in mineralogy. But we do see coordination 3. Oh, we could put a line maybe across. Okay, so here we go. Coordination 3. This is called a triangular coordination number. Our radius ratio is anywhere between 0.155 through 0.225. So if your radius ratio calculation drops you in between that range, then you say, we have a 3 coordination number. We call that triangular. Our drawing would be 1 cation surrounded by, try to draw them as clean as you can here. Oh, I glitched out. That was a glitch in the computer. That was not my fault. All right, we drew 3 circles like this. And there it is. We have a triangular coordination. Now, in mineralogy, this is actually very important. All of our carbonates, or let's say it this way, many of our carbonate, the structure of the carbonates, the calcium bonded to 3 oxygens, I guess I should say it this way, 3O CO3 2 minus, CO3 2 minus, there we go. That forms that structure. So this one's very important in minerals like calcite and my favorite, rhodochrosite. All right, we're going to step in through more of them. 4 is the next coordination number. This one is called tetrahedral. Tetrahedral coordination. It occurs anytime you have a radius ratio between 0.225 and 0.414. This is so important because the silicates, and importantly, it's actually the silica tetrahedra. I'm going to introduce that term to you right now. Silica tetrahedra, which is the building block for all the silicate minerals, forms with this coordination. Now the way that this looks, the silica tetrahedron is SiO 4. So what we need to do is we're going to draw a tetrahedron here where we have a silica that sits in the middle, and it is bonded to 4 oxygens. There's one oxygen, 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 and oxygen. Okay, so here's our oxygen anions surrounding that, and we could draw in probably the shape here of this, where because a tetrahedron is a shape of 4 triangles, right? So there's one triangle, the triangle on the base, the triangle on the side, and then the triangle on the back. All right, so this would be a silica tetrahedron, and it would be, what do we have? We have Si. Si is 4 plus, and so that needs to be balanced by the oxygen 2 minus. So each oxygen is transferring 1 minus in to balance off the 4 plus. All right, a lot of information just from tetrahedral coordination. Next coordination, there's just a couple more of these. We'll go coordination 6. This one is called octahedral. Octahedral coordination. Now this gets a little complicated. Why is it 6? Well, this sounds like 8. Well, there's a reason for it. An octahedron has 6 apices or corners, but it has 8 faces. Okay, so the 6 corners octahedral name. Sorry if that's a little confusing. Our thresholds here are 0.414 to 0.732. Mineralogically, there are a lot of silicates that have octahedral coordination, especially when the cations get a little larger. So let's say there's a silicate with iron or magnesium and the SiO4. Well, then you'll have tetrahedrons and octahedrons within the crystal structure. Something like halite could be another example that forms with this structure. And the way this looks, well, it starts to get a little more complicated, right, with each progressive drawing. But if we just drew an octahedron here first, then we could fill in the corners maybe next. All right, so if there's our octahedron, put dash in the backside here, we get our corners. How many are there in green? All right, there's 6. That's why it's a coordination of 6 surrounding that one central cation. The last one that's actually really important is called cubic, and it has 8 apices. Right, that's the way to think about the number. Cubic has a threshold of anywhere between 0.732 and 1. Our minerals that have it, well, these are the largest, any kind of mineral with the really big cations. Maybe something like sodium would have a cubic coordination number. The shape we want to picture here is a cube. We've drawn these many times, so go ahead and let's draw the cube, and we'll put in the corners after. Dot, 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 dot. We just did this for fluorite, right? So that could be this example here. Just as a recall, we have fluorite, which we have our F minus in there, and then sitting inside, surrounded by 8 fluorines, is 1 calcium. And then our last example, that I guess we've sort of already introduced, right? When you have 12, it's the maximum you can ever have. Well, this is called closest packing. This is when you have a radius ratio of 1 or maybe even bigger than 1, and this is something that is very rare, and it's too hard for me to draw, so I'm not going to try to draw it for you. That table is this table, right? On page 72, figure 4.4 in your textbook. I wanted to make you work for it, but here's kind of a nice cheat sheet that goes through everything that we just did, and maybe the drawings are a little cleaner. So then before we leave off today, there's just 2 last things I want to mention about coordination. And one is that distortions are possible. It's not like most of the time it works out, but it doesn't work out every time. And so sometimes distortions are possible. And what I mean by distortions is that this is like the radius of an ion might change. We'll say this, radius may change as a function of bonding and the electron cloud environment of bonding and electronic environment. And maybe you won't know the size of the radius. You might not be able to pull it perfectly off a table. So most of the time, you just go to a table, you make your calculation, you figure out your coordination number. But there are times when that rule gets broken. Don't be surprised by it, but I'll always let you know if that's going to be a case. And then I guess the last thing to talk about is what happens if you land right on a boundary, right on the threshold? What can happen? Well, that does happen in nature, and you get a situation called polymorphism. Polymorphism. This is a time when you have two minerals that are structurally totally different, but chemically they're the same. And the example we have here is calcite and aragonite. They both have the chemical formula of CaCO3. They both occur in nature, right? You've probably heard of them. I don't need to explain them. But calcite and aragonite, they're polymorphs of each other. They have different crystal structure, but the same chemical formula. And what ends up happening for aragonite and calcite, let's just do this. Let's go aragonite and calcite. Aragonite has a coordination number of 8, so it's cubic, and calcite has one that's 6, so it makes it octahedral. Well, what ends up happening is the ratio of calcium to oxygen has a radius ratio of 0.714, which is very near the threshold. So if we were to like draw this, the threshold 732, anything less than that is 6, anything greater than that is 8. And so CaCO3 falls kind of like right here. And so sometimes, depending on the temperature or the pressure of the geologic environment, you can actually go to either side of this line, allowing for polymorphism. All right, well, that's it for this lecture. Thanks for sticking with me. See you next time.